A ceiling isn't just a ceiling, it's a fire barrier, and every downlight cutout changes it. Downlights look brilliant, but cutting holes in ceilings can compromise fire performance, which is why fire-rated downlights matter. So today, I'll show you how they work, what the rating really means, and what to get right when installing them. Then we'll go beyond compliance, because once the fire side is sorted, the real spec decisions begin. And that's where you separate a commodity downlight from a specialist one. Most ceilings in UK homes follow a pretty standard build-up. You've usually got timber joists and then your ceiling lining. In most modern houses, that's plasterboard with a skim finish. And that plasterboard isn't just there to make it look good, it plays a huge role in fire safety, because a ceiling isn't just a ceiling, it's a fire barrier. In the UK, fire safety guidance sits within approved document B, and one of the key ideas is that elements of a building, like floors and ceilings, need to provide a period of fire resistance, typically measured in minutes. In a typical domestic setting, that baseline is often 30 minutes, meaning the structure should resist fire long enough to maintain its integrity and help limit spread between levels. Now, plasterboard is a big part of that performance. Gypsum contains chemically bound water, and when it's exposed to heat, that water is driven off as steam, absorbing energy and slowing the temperature rise. But here's the problem. The moment you cut a hole for a downlight, you've broken that barrier. Instead of one continuous fire resisting layer, you've now created an opening, and in a fire, flames and hot gases will take that shortcut straight through. And in downlighting installations, it's rarely just one hole. You're often putting in multiple cutouts across the room: kitchens, open plan spaces, lounges, and each one of those penetrations is another potential weak point in that ceiling barrier. So that 30-minute ceiling performance you're relying on, it's only as good as its weakest point.
About 15 minutes on it.
And that's exactly why fire-rated downlights exist. A fire-rated downlight is designed to restore the integrity of the barrier around the cutout and prevent that opening becoming a direct pathway for fire and smoke. Now here's the important bit. The rating isn't validated by testing a downlight on its own. To prove performance, downlights are tested at a fire performance test centre as part of a full ceiling and floor structure. Plasterboard joists the upper floor build-up and a load that reflects a typical housing construction. And the whole assembly has to last the duration of the test without collapsing. So the test isn't just about the downlight, it's about how that downlight performs as part of the overall structure. It's a system test. And this matters even more today because modern construction methods rely heavily on engineered timber, often I-joists or metal web joists, depending on the system. Engineered timber has loads of advantages for builders. It's lighter to handle, more consistent, more stable, and it makes it easier to build straight and fast. But it's also important to understand that these engineered joists don't necessarily have the same endurance in a fire as traditional solid timber joists, which is why the ceiling lining and the test evidence become even more critical. That's also why many building warranty and insurance providers, such as the NHBC, will expect to see a test report that proves performance in a specific manufacturer's ceiling system. And it's why some manufacturers like Collingwood have validated a wider range of downlight options across many of the commonly used floor and ceiling joist systems, because what matters is proven performance in the system you're actually fitting into. And this is where it gets really interesting. The 30-minute test is often the most onerous because it relies heavily on the whole structure performing well with relatively thin plasterboard. With 60 and 90-minute constructions, you tend to have thicker boards and more layers, so the performance relies more on the lining build-up. Let's look at how the construction of an LED downlight helps maintain that fire barrier, because one important point to understand is this. In a real fire, temperatures get so high that a lot of the materials in the fitting don't stand a chance. Plastics soften and fail very quickly, and even aluminium components can lose strength and melt. That's why most fire-rated downlights rely on something much tougher, a steel can held tightly in place within the ceiling using strong spring clips. And yes, the springs are so strong, they're basically a mousetrap for your fingers. And if you've ever had one ping back on your finger, you'll know exactly what I mean, but there is a reason for it. Steel has a melting point typically in the region of 1370 to 1540 degrees Celsius, depending on the grade. Aluminium, by comparison, melts at around 660 degrees Celsius. So even when other components deform, soften, or disappear completely, that steel can, with minimal openings, continues to block the passage of flame and hot gases through the cutout for the duration of the rating. This is the approach generally employed by Collingwood Lighting across their range of fire-rated fixtures, using a robust steel can held tightly in place so the ceiling barrier isn't completely compromised by the cutout. Now, there's a debate that always splits opinion when it comes to downlights, and it's this. Do you go for integrated LED downlights, meaning a dedicated LED fitting with a light engine and a separate driver, or do you go for what's often called a lamp and can fitting? The lamp and can approach is basically a downlight body that was originally developed to house MR16 or GU10 halogen lamps, so the idea was simple. When the lamp expires, you swap it out. And at first glance, that still sounds like a serviceable solution, because if an LED lamp fails, you can replace it. But it is a compromise, because when it comes to fire rating, an LED lamp has its driver electronics built into the lamp body sitting right behind the LEDs. That electronics produces heat, the LEDs produce heat, and in a lamp format, there's a very limited surface area for that heat to escape. And once you place that lamp inside a fire-rated can, airflow is reduced even further. So the lamp runs hotter for longer. That has three knock-on effects. First, it can affect reliability and lifespan because heat is the enemy of LEDs and electronics. Second, it compromises overall lighting efficiency because the hotter the LED runs, the less efficiently it produces light. And third, and this is the big one, thermals limit the power. So lamp and can setups are often restricted to lower light outputs compared to integrated fittings. In other words, you might have a downlight that's fire rated, but you're capped on lumen output because the lamp simply can't shed heat effectively inside that enclosure. So manufacturers have to create a balancing act. To allow ventilation, they often include holes or vents in the back of the can, but those holes can't just be open because they'd become a direct pathway for fire and smoke. So what they do is fit those ventilation points with intumescent material, a compound that expands rapidly when exposed to high temperatures, sealing the openings to block the passage of flames and hot gases during a fire. So fire-rated performance isn't just about steel can good, it's about how the design manages two opposing requirements: ventilation and heat management during normal operation, and sealing the cutout during a fire. And that's why different downlight designs behave differently. And hopefully you'll appreciate from that demonstration just how important fire-rated downlights are in preserving the integrity of ceilings during a fire. The footage you've seen in this video in our makeshift setup here is nowhere as intense as you'd get in a proper test centre, but it's interesting to see that we managed to drive our ceiling with the holes in to collapse in less than 20 minutes. But a ceiling isn't only a fire barrier, it also plays a role as an acoustic barrier, reducing noise transmission between rooms and between floors. And in many constructions, it also acts as part of a vapor and air barrier, helping control condensation, drafts, and uncontrolled air leakage, which ties directly into the building's ventilation and energy strategy. So when you install a downlight, you're not just cutting a hole in a fire barrier, you're cutting a hole in the overall performance of the building fabric, which means you can end up affecting more than just fire performance. You can also impact other parts of the building regulations. Part E, sound insulation. Part C, moisture and condensation control. Part L, energy efficiency and air tightness. And it's for this reason that downlights, especially more specialist ones, often include additional design features beyond fire rating. For example, you'll often see a gasket around the trim designed to seal against the plasterboard that helps reduce air leakage, limits moisture movement through the cutout, and helps keep the ceiling performing the way it was originally designed to. And here's the practical takeaway. Don't just assume a downlight helps with those other requirements. Check the manufacturer's specification sheet. If it's genuinely designed to support compliance with things like air tightness, moisture resistance, or acoustic performance, the manufacturer should state that clearly and ideally back it up with test evidence or system approvals. Of course, the nature of buildings is that insulation is often used, either to improve thermal performance, acoustic performance, or both. And the moment you install downlights, you risk compromising the integrity of that insulation layer. Now, many downlights can be installed and safely covered with insulation, but don't assume that's always the case. Look for the relevant insulation coverability symbol on the fitting itself and check the specification sheet for exactly what type of insulation it's approved to be covered by, because coverable can mean different things depending on whether it's mineral wool, rigid board, or other insulation types. And in some cases, the clearance requirements still apply. Also, remember, many downlights use a separate electronic driver, and best practice is to make sure that driver sits above the insulation, not buried underneath it, because drivers generate heat, and if they can't shed it properly, they'll run hotter, fail earlier, and shorten the life of the whole system. Now, let's get back to the main reason anyone fits a downlight in the first place, to actually light the space. But before we move away from building regulations, there's one that's directly linked to lighting, and that's Part L, which is all about energy efficiency. And Part L isn't just about using LED instead of halogen. It pushes two key things. First, your fittings need to be efficient. In domestic installations, the guidance sets a minimum lighting efficiency requirement of 75 lumens per watt for fixed internal lighting. Most modern LED downlights can achieve that, but it's still worth checking the datasheet because not all of them do once you factor in drivers, optics and thermal limits. Second, and this is the bit people forget, Part L is also about not overlighting the space, because energy efficiency isn't only about lumens per watt, it's also about how many fittings you install and how hard you're driving them. So if you're throwing 12 downlights into a small kitchen just because that's what everyone does, you might be compliant on efficacy, but you can still waste energy and often end up with glare and a really unpleasant lighting effect. A better approach is work out what the room needs, choose efficient fittings and space them properly. A quick word on energy labels, because a lot of people still get caught out by this. The AG system was rescaled in 2021, so products that would previously have been A+ or A++ are now often labelled E or F. So seeing an LED product with an E or F label doesn't necessarily mean it's inefficient. Of course, it's just the way the new scale works, but energy efficiency does matter. Part L sets a clear baseline, but lighting isn't just about energy. We also want rooms to be well lit with the right lighting effect, the right ambience, and the right visual comfort. And once you start designing lighting properly, you'll see that some of the things that make a space look better can reduce efficiency slightly, but the end result is worth it. Because if you focus on efficiency alone, you can end up with a room that's technically compliant, but looks awful. So let's look at a real example. Take this Collingwood H2 Deco CSP. Like many modern LED downlights, it has switch selectable options, both for power output and color temperature. And you can see from the specification data that choosing a higher power output gives you more light, but efficiency can drop slightly. And choosing a warmer white also reduces efficiency slightly. That's completely normal with LED technology. But the key point is, at all settings, this downlight still meets the 75 lumens per watt requirement for Part L. Now, notice what happens as efficiency changes. It's mainly the lumen output that drops. So if you're designing to a specific light level, warmer color temperatures, like 2200 Kelvin, can mean you need more fittings to achieve the same brightness. And color temperature is usually chosen to match the application. 4000 Kelvin is ideal for task-based areas, crisp and functional. 3000 Kelvin is the go-to for kitchens, clean and natural. And 2200 Kelvin is perfect for a lounge when you want that cozy, warm feel. So Part L gives you the minimum efficiency target. But from here, it's the lighting design choices, color temperature, beam angle, glare control, diffusion and dimming behavior that determine whether a room just has lights in it or whether it actually feels properly lit. And if you'd like to understand more about those lighting design terms and parameters, we've got a separate CPD module that explores them in more detail. Definitely worth watching after this one. All of these parameters are closely related to lighting design, and there are a few design features on some downlights that can genuinely improve the overall lit effect. Because in a lot of installations, downlights just get placed on a regular grid pattern, often with too many fittings. It's what we sometimes call ceiling acne. Now that approach does have its place, especially if you need a very uniform spread of light across a room. But if you know how a room is actually going to be used, you can get a much better result by positioning downlights with intent. For example, you can align lights to highlight a dining table, you can place fittings closer to a wall to throw light down it and add depth, and you can use light to draw attention to features in the room, rather than just trying to blast the whole ceiling evenly. Those small changes can dramatically improve the feel of a space, and often you can achieve a better result with fewer fittings, not more. Now, one of the biggest upgrades you can make to the way a room feels is to think about glare. One of the best rules of thumb is people in the room should see the lit effect, not the source of the light. And with downlights, we can achieve that by using a low glare design like the H2 Deco CSP. In these fittings, the light source is set back deeper into the body, so once it's installed, people don't get that direct line of sight to the LED, which massively reduces discomfort glare. And you can take it even further by swapping the inner bezel to a black finish, which helps absorb stray light and makes the fitting visually disappear into the ceiling. In more technical lighting design terms, this is glare control, and using a low glare downlight like this can help achieve glare ratings of UGR less than 16, which is especially useful in spaces where people are working with screens. Now, there are a few further techniques that can elevate the lighting design even more, and this is where stepping up to a more design-focused downlight starts to make sense. For example, these Collingwood 1901 fixtures have the low glare attributes we've just discussed, but they also allow you to specify different beam angles, which controls the shape of the light leaving the fitting. Most downlights used today tend to have wider beam angles for general lighting, and that's great for even coverage. But by opting for a narrow beam, you can create accent lighting and make a feature of something in the room, a plant, artwork, or an ornament, without having to add separate spotlights. And finally, we spoke earlier about dimming and color temperature. And one premium feature that combines both is something called dim to warm. This is where, as you dim the light down, the color temperature shifts warmer, mimicking exactly what you used to see with halogen and incandescent lamps. So rather than just going dimmer, the light becomes more amber and cozy. And for example, shifting from 3000 Kelvin down to around 1800 Kelvin, giving a warm orange glow. And that can completely change the atmosphere in a room, especially in lounges, dining spaces, and anywhere you want lighting to feel comfortable rather than clinical. So once you've covered the basics like fire rating and compliance, this is where the real difference shows between a commodity downlight that simply lights a room and a specialist product that gives you control over how the room feels. Now, it's worth saying downlights should really be just one tool in your lighting toolbox. They work best when they're combined with other techniques. In a kitchen, for example, downlights are often supported by under cabinet lighting for the worktops and maybe pendants over an island or dining table. In a bedroom, you might use downlights for general light, but then rely on table lamps or wall lights for softer ambient lighting. And there are also situations where you should actively avoid downlights. One question we get all the time is, how do you install downlights in a sloped ceiling or a ceiling packed with PU foam insulation? And the honest answer is, in many cases, you shouldn't, because downlights on a sloped ceiling can be a recipe for glare. The light source is far more likely to end up in your direct line of sight, especially when you're sat down in the room. And if the ceiling is insulated with spray foam or rigid PU insulation, you've got another problem. You end up having to dig out insulation just to create a void for the fitting. So you're cutting into the building fabric, reducing the effectiveness of the insulation, and you're potentially creating thermal weak points, which is the opposite of what you want. A much better solution in those situations is to use a surface-mounted spotlight like the Collingwood 1901, because you're not cutting into the ceiling, you're not disturbing the insulation, and you can tilt and aim the light exactly where it's needed rather than blasting light straight down and hoping for the best. So yes, downlights are brilliant, but part of good lighting design is knowing when not to use them. Of course, downlights can also be used outdoors, in entrance porches, covered walkways, and building soffits. And in those locations, fire resistance isn't usually the big concern. The bigger issue is water ingress. A lot of downlights already have an IP rating because they're designed for bathroom ceilings. Take this Collingwood H2 Light Select, for example. It's an entry-level downlight, and it's a great choice for bathrooms and toilets. Now, if you look at the specification sheet, you'll notice it has two IP ratings, IP65 and IP20, and this is where people can get caught out. The IP65 rating refers to the front face of the downlight, the part you can see inside the bathroom, which is exposed to moisture, steam, and splashes. The IP20 rating refers to the rear side of the fitting above the ceiling, which in a typical bathroom ceiling isn't directly exposed to moisture in the same way. So in simple terms, IP65 from below, IP20 from above, and that's usually fine for bathroom ceilings, but it's not the same as an outdoor soffit, because in a soffit installation, moisture can get to the fitting from both sides. Wind-driven rain, cold air, condensation, and in some cases water can track back into the ceiling void. So for soffits, Collingwood make a dedicated fitting that's sealed both ways. The H2 Pro Extreme, which is IP65, rated from the front and the rear. So the takeaway is, always check whether the IP rating is front only or both sides, and match the product to the environment, because an IP65 bathroom downlight isn't automatically an IP65 soffit downlight. So hopefully you now understand why fire-rated downlights matter, not just as a tick box product, but as part of maintaining the integrity of the ceiling as a fire barrier. And you've also seen that once the compliance side is covered, the real difference is in the specification, things like glare control, beam angles, dimming behavior, color temperature, and features like dim to warm, all of which can elevate the feel of a space and the finished result of your next project. I'll leave links in the description so you can learn more about the downlights we've used in this video. And if you want to validate what you've learned as part of your ongoing professional development and CPD, click the link in the description and it will take you across to our training platform. I'd love to know what you want us to cover next. What's the biggest lighting challenge you're seeing on site right now? Or what's one thing about downlights and lighting design that still feels unclear or gets argued about? Drop it in the comments because we use that to shape future lighting content. One other clever product from Collingwood you might be interested in is this H2 Sense, which integrates a PIR sensor into the downlight itself. It's ideal for smaller rooms like utility spaces, toilets and cupboards, helping reduce install time, cut costs and save energy. You can learn more about it in the video on screen now.